So this is office hour number 7. Next week will be the last one, office hour number 8. So I'm going to just review a few of the things that you're going to be looking at this week as you do your homework. Chapter 9 is due Wednesday night for the Pearson homework, and then of course there's the quizzes on Friday night. And the workshop should also cover these topics as well, which is due tomorrow night. So now next week will also be the last workshop. Instead of being Tuesday next week, I'm going to put it off toward the end of next week so that we can include just some Chapter 11 material on there as well. All right, so I'm going to talk about Chapter 9, concentration, and a little bit of Chapter 10, which is kinetics and equilibrium, and try to tell you what the most important parts of those chapters are. So Chapter 9 is about solutions, and so when you dissolve things, you need to understand how they dissolve and why they dissolve. And so basically there's a rule that says like dissolves like, and you have to know how they're alike from their structure. So the next topic is concentration as a concept. The more stuff you have dissolved in a solvent, then the more concentrated it is. And so the concentration is the amount of the thing you're dissolving, the solute, divided by usually the amount of solution. And so the units of the amounts can be grams, mass, volume, liters or milliliters, and then moles. Now the mole unit is really only for the numerator. So the book covers several different examples. One is mass percent, mass over mass. So the mass of the solute divided by the mass of the solution, which is solute plus solvent. Volume percent, which is volume of the solute divided by the total volume. And then a mixture of the two, which is the mass of the solute divided by the volume of the solution. I won't do too many of these sorts of problems. The most important concentration unit for a chemist is this one here. It's molarity, and that's moles per liter. So if you see so-and-so percent solution, it doesn't say what the units are. It's implicitly the mass over the mass. Okay, and so after you learn how to do calculating concentrations in different units, then every one of these can be a conversion factor, because remember, a conversion factor has a numerator that's equal to a denominator in some way. Well, mass percent saying, well, we've got so many grams of one part divided by 100 grams of another part, if it's a percentage. Or we have so many moles of solute divided by liters of solution, and we can convert one to the other using molarity. And so using those conversion factors, of course, a very important sort of skill, one of which would be the volume times the molarity is the number of moles. And that's why this particular unit is so important to the chemist. It's because we can, instead of having to calculate grams to moles or something like that, we already know the moles per volume in the solution, and we can just measure out a certain volume. So let's just do a quick example. So how many mole? This is not a good marker. Let me try this one. How many mole of HCl and 250 mils of 6 molar? Okay, and the other thing to note is the way we write the unit. Moles per liter is capital M. So this is 6 moles of HCl per liter of solution. So the actual way you pronounce this is 6 molar hydrochloric acid, or HCl. All right, so this is 0.25 liters. That's the volume. You multiply it by the molarity, which is 6 moles per liter. The liter units cancel, and I'm left with moles. and 6 times 0.25 is 1.5. Oops, 1.5. Not an extra zero. Okay, of HCl, the solute. So when you're working this, make sure you're clear on what solute is in your solution and what the solution entails. It's usually water plus the solute. Now, in order to do a dilution, you can use this particular relationship here. It's based on the fact that when you add water to something, the number of moles of material is still there, still the same. So if you take a can of frozen orange juice, it's got so much sugar and so much, orange pulp and stuff in there. And then if you follow the instruction, you add some water, still, the whole thing still has the total same amount of sugar. You didn't add any sugar, none goes away or anything like that. And so the concentration in any units, actually this equation will work for any units, mass percent or volume percent or whatever, times the volume equals the concentration times the volume for the dilute. So for the concentrated, if we call the variables with subscript 1, the concentrated, these will be the dilute. The volume of the dilute is much larger than the volume of the concentrated because the concentration of the concentrated is much higher than the concentration of the dilute solution. So there's inverse relationship. So if you take orange juice, for example, 1 can of orange juice stuff, then you add 3 cans of water, what you've done is quadruple the volume. And when you quadruple the volume, you cut the concentration by 4. Then the next part of the text talks about properties of solutions. And so the two that are really related to each other are the changing the freezing point and the boiling point. So we're just going to concern ourselves with water. Water freezes at 0 Celsius. It boils at 100 degrees Celsius. That is to say under standard atmospheric pressure. The change in the freezing point is a constant times the osmolarity. So we'll have to understand what osmolarity is, but you'll always be given the constant. And the constants for water is 1.86 degrees C per osmole. And so if you have a 1 osmolar solution, that is to say a mole of a non-electrolyte like sugar, so you dissolve 1 mole of sugar per liter, that's 1 osmolar. And changing the freezing point would just be whatever Kf's value is, which is 1.86 degrees. Now the freezing point goes down when you dissolve things in water. So that's why we add salt to roads, is because the freezing point of a salt solution is below the temperature that is causing ice to form on the roads. All right, and so we don't put sugar on the roads, though, to melt the ice. What we do is we put table salt or sodium chloride on the ice. So 1 mole of sodium chloride per liter actually produces 2 moles of particles. 1 mole of sodium ions, Na+, another mole of chloride ions, Cl-. So 1 molar sodium chloride is 2 osmolar. So to calculate for an ionic material the relationship between molar and osmolar, you have to multiply by the number of ions. Calcium chloride, which is sometimes used on the roads, is 3 ions. There's calcium 2+, and a chloride and another chloride. So there's a total of 3 ions here. So if the solution is 3 molar, then 3 times 3 is 9 osmolar. Right? So the osmolarity is the molarity multiplied by the number of ions when the thing dissolves. And if it's a non-electrolyte, it doesn't dissolve as an ion. All right, and so then it talks about osmotic pressure, which is why we have the word osmole. And it's done in a qualitative sense. We don't actually calculate osmotic pressures, but you're supposed to understand that if you have a highly concentrated solution in contact with a dilute solution, and there's a membrane between the two which allows water only to pass, but not the solute, then water will go from the dilute solution, or even pure water, into the concentrated solution, and that will expand and produce a pressure. cause the osmotic pressure. You can actually reverse this process by applying pressure to the high concentration solution. That's called reverse osmosis. But you have to realize that when you do that for water, you get pure water out. And so this is actually what's done with dialysis. Dialysis takes your dilute urine solution, exerts a pressure on osmotic membrane, pushes water out, and then that water goes back into your body, because the reason your kidneys exist is to take dilute urine and concentrate it into concentrated urine so that you don't dehydrate when you urinate too much. All right, and then I want to discuss a little bit about what to look for in Chapter 10. Chapter 10 is a kind of a short chapter, although if it's new to you, it doesn't seem to be that short. For the kinetics part, the main thing is you just have to qualitatively understand the three factors that make reactions faster. One is if you want something to speed up, you heat it up. If you want it to slow down, you cool it down. So a couple of examples of this is if you have somebody who's fallen into a frozen lake, the reduction in body temperature can actually slow down the processes enough in the body so that a time period that normally with no heartbeat or breathing would kill a person at room temperature, they may still be able to survive even without brain damage if they've been cooled down like in icy water for a long time. So temperature affects the rates of reaction. One is concentration. The more concentrated the solutions are, then the more frequently collisions occur between the things that are going to react, the faster the reaction will be. And then the last thing is something called a catalyst. So an example here would be if you have a bottle of hydrogen peroxide at home, it'll go bad slowly over time. It'll decompose to water and oxygen. But the rate at which it decomposes can be accelerated by using a catalyst. And one example of a type of catalyst is enzymes in the body. So the enzymes in your body accelerate chemical reactions. So you can actually see this. If you could take a piece of liver and drop some hydrogen peroxide on there, you'll see bubbling. And that bubbling is the catalysis for the breakdown of hydrogen peroxide, because there are enzymes in your body that actually break down hydrogen peroxide. They're called peroxidases. But past that, you're not going to be working any problems based on kinetics. Just the main thing is to understand what a catalyst is, what it does. Then equilibrium is introduced, and that's an idea that if you have a chemical reaction, and you can write an arrow where it's going from reactants to products, well, most of the time we just assume that it just stops there. But some reactions actually run also in reverse, okay? And equilibrium is the point at where the forward and reverse rates are the same. And so there are many, many processes in the body where both the forward and the reverse reactions go on all the time. So if you look at the molecule ATP and ADP in biology, well, your body uses ATP all the time, and it makes ATP all the time. As a matter of fact, you have to have both reactions going on, not necessarily in the same time in the same place, but they both need to occur, so which means that a forward reaction, if it's ATP going to ADP, well, you must be able to run the reverse reaction also to make ATP from ADP. And so that's the idea of equilibrium. Then learn how to write the equilibrium constant, K. It's really quite simple. There's a page in the book that says, here, if you have these coefficients in your balanced reaction, these coefficients become the powers in the equilibrium constant. The main thing to remember there is that the products are in the numerator and the reactants are in the denominator of this equilibrium constant. That's the most common error. The other thing you have to remember is the only thing that appears in an equilibrium constant is the things that can change concentration. Okay, so I've got two reactants, two products. The equilibrium constant for this is the product's concentration, which is denoted in the square bracket, so this homework is due Sunday night, and the workshop next week will be dealing with some of this acid-base stuff. CH3COOH. Okay. What we did not put into this expression was the water, because the concentration of water is the density of water, and that's not really affected by putting things in water. So if you add some acetic acid molecules to water, the density of the water is about the same. The water, as far as it's concerned, is just like water in pure water. And so it's the molarity of this to the first power, molarity of this to the first power in the numerator, divided by the molarity of this to the first power, the denominator. So all these coefficients are ones, which is why, we don't even write the first power of anything, because anything to the first power is just that number. And then how to work problems with that. And then the last topic is how to apply Le Chatelet's principle. The most important thing is how to apply Le Chatelet's principle by adding or removing one of the reactants or products. Okay, there's one for changing the temperature up or down, and then there's one for changing the volume. And then I can tell you that I'm not going to put anything on the final exam about how Le Chatelet's principle applies to changing volume. That's a little too complicated. But the main thing is to be able to use Le Chatelet's principle for changing temperature or changing the quantity of one of these guys. Okay, I believe I've said enough. So I was looking at the quiz questions for Chapter 10, and they seem to be mostly based on certain reactions like ammonia. The only reason I did those is because all these acid-base things, they have coefficients of 1. So I wanted to use some examples where wouldn't necessarily be coefficients of 1. The other thing to realize is that this is kind of an algebraic equation, right? So I've got 3 variables and then a constant. And so there's two types of problems. One's where I give you all 3 variables and you plug them in and get the number for the constant, or the other is more common, where you look up a constant and you're given some information about some of these concentrations and you have to find the missing one. And that's particularly important for buffers as we get later on in Chapter 11, which is really toward the end of Chapter 11. Okay, I got a question. Question 23 on the homework with vexing. All right, so a student said, okay, the homework question 23 was difficult and tricky because it involved something about the strength of bonds and which bonds are stronger or weaker. No, you do not need to know that. But I will tell you something about acids and bases that are related to bond strength. So the thing is with, say, acetic acid, there's an OH bond here. So let me draw the acid group. You have to break this bond right here in order to get an H plus off of it, which means you have to break the bond right here. Okay? Where both electrons stay with this oxygen, that's why this has a negative charge, and that's why this will have a positive charge. So how often this breaks is dependent on, of course, how strong this bond is. So the weaker the bond is, the more likely it is to break. So you're only going to be responsible for knowing which acids will break completely versus which will not. And I will talk more about that in Chapter 11, but Chapter 11 will talk about strong acids, and anything that's less than that is just going to be a weak acid. I'm not going to have you order the weak acids at least by some sort of chemical intuition about, all right, which bond should be stronger than the other. The other thing about the organic acids, these are almost all the same. So when you look at organic acids like citric acid and vinegar and malic acid and propionic acid, they're all about the same strength. Weak acids, some of them can definitely sour up your stomach though. But I'll talk more about that later. But if you see an equilibrium, that's by definition a weak acid. Strong acids, essentially the proton comes off and it's as H3O plus and it never goes back. And so strong acids, one-way arrow, weak acids, to an equilibrium. And the other clue is if there's an equilibrium constant, there's an equilibrium, which means it's a weak acid. If there's no equilibrium constant, or the equilibrium constant is very, very large, it's essentially a one-way reaction. The other thing is the magnitude of this number depends on the magnitude of the numerator and the denominator. The bigger these numbers are, the more acid H3O plus you have, the stronger the acid. So the bigger the K, the stronger the acid. So that's really relevant right now for things like hydrochloric acid, which is a strong acid. So if you dissolve that in water, if it's 1 molar, it'll be like sodium chloride. You get an H plus, 1 molar of that, and then 1 molar of chloride minus. This is much different. Basically, I believe it's a question about acids again. And so when you have a molecule, okay, most molecules are non-electrolytes. That's to say, when they dissolve in water, they stay together, they stay neutral, and it's one big old molecule, mostly through hydrogen bonding, or maybe if they're polar, they'll dissolve in water. There's a class of compounds called acids and another class called bases that when they dissolve in water create ions. The acids create H3O plus or protonated waters. The bases produce hydroxide, OH minus, and that's how they're defined as acids and bases. So you do have to eventually, by the time you get to chapter 11, recognize what makes something a base or an acid. If you have a salt with hydroxide, that's a strong base, if it will dissolve. That's the key. So the other thing about chapter 9 I forgot to mention is the solubility rules table, table 9.7, will be given to you on the test. So the question is hydroxide. Well, that's OH minus. In water, that makes it very basic. Well, sodium hydroxide dissolves as these two ions. So sodium hydroxide, strong base. Don't mess with this stuff. This is extremely dangerous. You get it in your eye, you'll go blind. Whereas aluminum hydroxide, it's made from hydroxide, but it won't dissolve in water. And so that's why you need to know the solubility rules. So yes, this would be a base, but it won't dissolve in water. So it'll only react with acid as a solid. So you do need to be able to recognize if you have a hydroxide, if it's soluble or not, based on the solubility rules. Basically, anything with group 1, like sodium, potassium, lithium, and ammonium, those hydroxides are reasonably soluble. The rest of the hydroxides are insoluble. So any of the transition metals, group 2A metals, all those hydroxides are insoluble. So for example, magnesium hydroxide is called milk of magnesia because it's a white solid suspended in water. It won't dissolve in water. And then weak bases are anything with a nitrogen lone pair. And so those are called amines. And so this is always going to, so if you have any sort of molecule with an N and a lone pair, it's going to be a weak base. At least that part of the molecule is going to be weakly basic. then of course there's the acid groups. If you see an organic acid, weak acid. Strong acids, there's going to be a list. And I'll tell you what that list is when next week I'll review that. Strong acid, strong base, weak acid, weak base. That's all chapter 11 stuff. So if you've seen anything kind of similar to that beforehand, well, to get you ready, because chapter 11 is pretty important. A lot of important molecules are acids and bases. Amino acids, for example. The amine part is a base. The acid part's a group, acid. Okay, it won't dissolve because the solubility rules. So you look at table 9.7 in your text, and you look for a rule about hydroxide, OH minus. There is none. Okay? So there's no rule that says hydroxides are soluble. Then you go look at the cation, aluminum 3 plus. Is there a rule for aluminum 3 plus that says it's soluble? And the answer is no. Well, if something's not on the table, it's not going to be soluble. Okay? So, but sodium hydroxide, the way it works is, okay, is hydroxide listed in the table? And the answer is no. Okay? We've already said there's no rule for hydroxide. However, there is a rule for sodium. So you look in the table and it says all sodium salts are soluble. So it doesn't matter what the anion is for sodium. It's going to dissolve in water. So if one of the two ions has a rule in that table that says it's soluble, the compound is soluble. Aluminum hydroxide has no rule for either the hydroxide part nor the aluminum part, so it's not soluble. This is soluble because sodium makes it soluble. That's how that table works. So you got to learn how to use the table, but you don't have to memorize the table. So yeah, this is the reason they're insoluble. So aluminum's 3 plus, so it takes 3 hydroxides to dissolve, not dissolve, but to form a neutral salt. And so that's why it has the formula it does. As a matter of fact, I will say aluminum hydroxide in high concentrations you can dissolve aluminum. So you don't want to add concentrated sodium hydroxide if you have aluminum. It will dissolve it. So if you ever buy the Drano, the solid stuff, it has a little flecks of metal in there. That's aluminum. And so the reason that's in there is because aluminum does react actually even with sodium hydroxide. And so it gives some things, some additional stuff. It's not, if there's metals dissolved in water, what they'll do is they'll add hydroxide, adjust the pH by adding hydroxide until you get a lot of precipitates of these insoluble hydroxides for the metal, filter it out, and then readjust the pH back to something reasonable. I got it, and thank you. Wow, that's a miracle. Remind you, I didn't say what happens with the boiling point, but the boiling point actually gets elevated as the concentration increases. And so an example there is if you ever make candy, so you have a great big ton of sugar dissolved in water. You start to boil it, and it'll start boiling way above 212. It'll start boiling at 220 or so. And as the water evaporates, the sugar becomes more and more concentrated, and the boiling point goes up as you keep boiling this sugar solution. And candy thermometers tell you, basically says, okay, if your sugar boiling point is 234 Fahrenheit, if you stop and put the, pour it out, you'll get a caramel, maybe. Whereas if it's 237, maybe it'll be hard and brittle, like hard candy. So boiling point always goes up. If you know this about candy thermometers and what kind of temperatures sugar solutions boil at, you'll know that the boiling point always goes up. And so you calculate the change in the boiling point and you add it to 100 C to get the change in the boiling point. To get the change in the freezing point, it's a different constant. Okay, you'd be given KB. So boiling is B and B rather than F and F for freezing. Temperature goes down for freezing point, goes up for boiling point. It's a good thing for antifreeze too, right? You don't want your coolant in your car freezing at 32 Fahrenheit. See, this whole osmolar thing's related to electrolytes and non-electrolytes, right? So the reason they're called electrolytes is because they form charged ions when they dissolve in water. That allows them to conduct electricity. So pure water does not conduct electricity very well, whereas our bodies really conduct electricity quite well because we're full of electrolytes.